Hello students, welcome to MEC 1321 Engineering Statics. My name is Dr. Stewart, and today we're going to start Chapter 7, which is titled Internal Forces. The objectives that we have for Chapter 7 are to show how to use the method of sections to determine the internal loading in members, and to generalize this procedure by formulating equations that can be plotted so that they describe the internal shear and moment throughout a member. So today we're going to go and do section 7.1 and 7.2 from the book. 7.1 is titled Internal Loadings Developed in Structural Members, and section 2 is titled Shear and Moment Equations and Diagrams. So let's go ahead and get started with 7.1, Internal Forces Developed in Structural Members. So say we have a beam, some kind of continuous cantilever beam, and we decide to use the method of sections at some point along that beam. When we actually apply the method of sections and we examine the left-hand side and the right-hand side, we'll find that certain internal forces and moments will develop. And these internal forces and moments are required for us to maintain equilibrium. When we take a slice of that cantilever beam, say we take the left-hand side of the section, we'll find that three types of load develop. A normal force develops, which is a force that goes along the direction of the beam. A shear force develops, which is transverse to the direction of the beam. And both of those forces prevent the translation of the body. And then a bending moment develops, which prevents the rotation of the body. And these three internal loads, consisting of two forces in one moment, are what allow for an equilibrium state within this member despite the sectioning, right? And these are considered the internal loads that would, or internal forces that would develop in a member. So what we would do when we have a problem like this and we need to determine the internal load is we'll apply the method of sections, we'll identify or we'll list our internal forces and our given known forces, and then we'll do the sum of the forces and the sum of the moments to calculate what the value of those internal forces are. Now, it's important for us when we're trying to solve these problems of internal forces to recognize the sign conventions for these internal forces. What is positive and what is negative? And it's a little bit different than what we're used to. Or it's a little bit different than the sign convention that we've used previously throughout the book. So let's go ahead and examine that. The first thing we want to do is see the normal force. So a normal force is going to have a positive sign if the normal force creates a sense of tension, right? So if we were to do a section of a beam and we saw that there's some normal force that develops, if we are going to assume initially a positive normal force, then it should create a sense of tension in each member or each section of the geometry. And of course, if we were to take those sections and add them back together, then that internal force should disappear, right? So for each section, the internal forces should be equal and opposite, right? So now, what about shear forces? The shear force is positive if the shear force on the section would cause a clockwise sense of rotation. Notice that it's not counterclockwise, but a clockwise sense of rotation. Now let's look at what we would see in terms of our section. If we were to take a body and do the method of sections, a positive shear value would produce a clockwise sense of rotation, right? So notice the left-hand side has the shear value going in the negative y direction, and yet it creates a clockwise sense of rotation. Note that the right-hand side of the section has an upward pointing shear value, an upward pointing V, so a positive V, and it's creating a clockwise sense of rotation at some distance, right? So, and then also notice if we were to take a double section, so say we were to section both ends of a beam and took the central section, notice that the shear forces create a clockwise sense of rotation. It's very important for us to be able to distinguish what type or what is the positive sense for shear forces. And notice only when we're doing these internal force problems, or when we're doing the shear diagrams and moment diagrams, do we identify, only with the internal forces do we identify this clockwise sense for our shear value as positive. So do not confuse this with the method that we've done in the past for regular problems. So now let's go ahead and look at bending moments. A bending moment is positive if the moment will cause a concave upward bend. Okay? Now, what is a concave upward bend? Well, let's look at let's look at a beam. Let's do the method of sections, and let's put that internal moment that develops in the beam. The moment is positive if it would create a concave upward beam. If the beam was to bend concave upwardly, then we have a positive moment, right? So notice the left-hand side, we have counterclockwise sense, right? So the moment is for the left-hand side of this diagram. We have a counterclockwise sense, left-hand side, counterclockwise rotation. And then the right-hand side, we have a clockwise rotation. And yet both of these are producing concave upward bends, and so the moments are positive. Okay? Now if we were to take a central section, so if we were to section something twice and have a central section, then we would be able to identify the moment as positive if it creates that, again, concave upward shape in the relevant section. Okay? So a bending moment is positive if it will create a concave upward bend. And then to identify the negative signs, all loads that have an opposite convention to the ones that we've just identified are going to be considered negative, right? So if the normal force is under compression, then it is a negative value for normal force. If the shear force creates a counterclockwise sense of rotation, then it's a negative shear force. And if the moment creates a concave downward bend, then it is a negative internal bending moment that develops. So it's very important for you to become comfortable with applying this sign convention, which is particular to internal forces and the shear and moment diagrams. If you do not take the time to practice this and to remember this, then you will get your solution on your exams and on your quizzes will be completely and absolutely wrong. So it's very important that you identify this sign convention and are comfortable with using it. So what is the procedure for actually determining these internal loads? The first thing that we want to do, of course, is identify our knowns and unknowns, draw our beautiful free body diagram, list all our known forces. The method of section can be used to determine the internal loads on the cross section of a member, and we can use the following procedure. So before the member is sectioned, it may be necessary for us to determine the support reactions, right? So depending on which section we are interested in looking at, whether it's the left-hand side or the right-hand side, we may need to determine the support reactions. So we may need to free the body from its support and calculate the support reactions. If so, then we need to take the entire free body diagram and use the sum of the forces, use our equilibrium equation, sum of the forces, sum of the moments, to find those support reactions. Once we've done that, then what we can do is we can move into the method of sections. We can use the sum of the forces for each section, the sum of the moments. Ideally, what we'll do is we'll assume our internal forces are positive. So we'll assume tension, we'll assume clockwise shear, and we'll assume concave upward internal moments. And then we'll use our equations of equilibrium to solve for those internal forces. And from that, if we get a negative sign for those internal forces, then we know that the sense that we initially assumed is wrong, and that the internal forces are acting opposite to our initial assumptions. And then from there, we know the internal forces at the section that we found. Now, it's important to note that when we do this, when we do the method of sections, that the internal forces we find are going to be exactly the internal forces that develop along the line at which we section. And with a beam and with most objects, depending on where you section that body, the internal forces will change. The internal forces are not always one continuous value across a beam. As we apply distributed loads and concentrated forces and all types of different types of applied loading conditions, along the beam we'll find different values of internal force. And this will require that we move into the next section, which is how do we craft a shear and moment diagram. So chapter 7.2 is reviewing shear and moment equations and diagrams. So say we have a simply supported beam or a cantilever beam. Both of these are pretty classic types of members where we can readily identify what types of supports develop within the member. A simply supported beam is pinned at one end and has a roller at the other end, and a cantilever beam is fixed at one end and is free at the other end. Now sometimes we want to design a beam. We want to design a beam to be able to withstand a certain type of or a certain amount of internal load. In order to design a beam, the internal shear forces and bending moments must be studied, and they must be studied at every point along the beam. Now, in general, the internal shear force and moments within a beam will be discontinuous, or their slopes will be discontinuous at points where distributed loads change or where concentrated forces or moments are applied. So if we're given a beam and we have a system of forces applied to it, that as we section, as we go across the length of that beam, the values of those internal forces are going to be discontinuous. They're going to continuously change. There's going to be either a continuous change or rapid changes and jumps in the value of the internal shear force and moments due to your applied loading conditions. And so what we can do is we can use a successive we can successively use the method of sections to describe the change in the internal forces across the length of the beam, right? So here's an example. Say we're given a simply supported beam, or a simply supported beam. It has some distributed load on it, and it has some concentrated force P, right? We can describe the internal shear and the internal moment loads with respect to the distance along the beam by creating shear and moment diagrams, where the shear diagram is the value of the shear of the internal shear force is the y-axis, and the distance or the length of the beam is the x-axis. Similarly, for the moment diagram, the y-axis is a value of the internal moment, the internal bending moment, and the x-axis is a position along the beam. So how do we use the method of section successively? Simply what we need to do is we need to create free body diagrams for sections of interest, or sections where we expect a different behavior in our shear and moment diagrams. So what we can do is we can look at this beam and identify some of those sections. We notice from point O to the distance A, we have this distributed load W. So we know that that is a point of interest where there's some interesting phenomena going on. So we want to do a section from O to A. And then we look from O to the distance B. We see that there is another applied load, this load P that is applied. So it would be very good for us to do a section from point O to point B. And then, of course, we want to see what happens at the end of the beam. So the beam's total length is L. So we want to do a section from O to somewhere between B and L. So section OL. So we want to take this member and we want to split it into 3 sections, which will allow us to examine the internal forces in between the various loads that are applied. Now, when we do that, we can create free body diagrams that describe the sections for each of these, the section of each of these method of sections that we plan to use. And what we'll do is we want to find we want to use the method of sections, but we don't want to use a value of A, B, and L directly. We want to use a placeholder term, a term that we can use to describe the slope of the shear diagram or describe the slope of the moment diagram, right? So in this case, we'll use X1 for O to A, X2 for OB, and X3 for OL, where X1 is somewhere in between OA, X2 is in between OB, and X3 is in between O and the length L, right? We draw free body diagrams. We assume that the distance that we're going to be using is X1, X2, and X3. And then we can directly apply our equations of equilibrium, meaning our sum of forces and sum of the moments, in order to describe the shear force or the bending moment in terms of the value of X1, of X2, and of X3. And this will give us an equation which describes the behavior of these moments, or the behavior of the moment within the position of interest, from O to A, from A to B, and from B to L. Okay? So, what is the procedure for analysis? How do we actually apply this technique? The shear and bending moment diagrams for a beam can be constructed using the following procedure. The first step are support reactions. We need to determine all the reaction forces and couple moments acting on the beam and resolve all the forces into components acting perpendicular and parallel to the beam's axis. So we need to be able to simply take our applied loads and identify the components with which they act. The next step is determining the shear and moment functions. So we need to specify separate coordinates x having an origin at the beam's left end and extending into the regions of the beam between concentrated forces or coupled moments. So again, remember, from O to A, from O to B, and from O to L, we're specifying some distance x, and distance x1, x2, and x3 that is in between the points of interest, which we'll use to craft our shear and moment equations, or the functions that describe their behavior within the range. So once we've identified these x positions that are in between the points of interest, then we need to section the beam at each distance x and draw the free body diagram of the section of one of the segments of interest. We need to be sure that the shear and moment are shown acting in their positive sense in accordance with the sign convention that we showed earlier, right? So we want to make sure that when we put in our internal forces that we assume them to be initially positive. Then the shear function is obtained by summing the forces that are perpendicular to the beam's axis. So we use the sum of the forces, and we'll be able to find a function of the shear force as it relates to our x value, whether it's x1, x2, or x3. And then we can also find the moment function and it's attained by summing the moments about this, the sectioned end of the segment, right? So doing the sum of the moments, and from that, we should find a relationship between the value of the bending moment and our X position, our X1 or X2 or X3 position. And now that we've got these functions, now it comes to us to actually create our shear and moment diagrams. Plot the shear diagram, which is the shear force versus the X position, and the moment diagram, which is the bending moment versus the X position. If computing values of the functions describing the shear and bending moment, if the computed values are positive, then the values are plotted above the x-axis, right? So we're going to assume it's in the positive direction. Whereas if our computed values from the functions we found are negative, then the value should be found below below the x-axis, right? And so it's important to note that for each section, we're going to find a different equation for our shear and our bending moment. For each section that we've created, there's going to be a different equation that relates to the X1, X2, and X3 position. And so we're going to use each of those equations for the relevant portion of the shear and moment diagrams. And generally, it is convenient to plot the shear and bending moment diagrams directly below the free body diagram of the beam. And this is convenient because you're able to very easily identify, okay, I've got a concentrated force here. There should be something going on in my shear diagram below that. And then below my shear diagram, there should be something going on below that as well, right? And we'll see some examples in class, and there are a significant number of examples in the book which should be able to give you a little bit more advice on how to apply this method. So with that said, I suggest that you read the relevant sections, section 7.1 and 7.2 from the book. There are a good number of example problems which will help you to better understand the procedure for implementing the method of section such that you can find the shear and moment diagrams. Make sure that you come prepared for a quiz. Our quizzes are going to be like exam style problems, so you do need to be comfortable with solving is a handful, at least some of the problems that are relevant for this section before you come to class. Thank you for taking the time for watching this video. I'm Dr. Stewart, and I'll see you in the next one.